All right, so with this one, number 17, recall that our moon is, um, from your reading, 384,400 kilometers away from the Earth, and it takes 27.3 days for our moon to orbit the Earth. Use the velocity equals distance divided by time, where distance, of course, is the circumference of the moon's orbit in kilometers. Convert the period to seconds and find the velocity of our moon in kilometers per second. All right, so let's do that one first. Part B is you're just verifying this using the orbital velocity equation, right? So I'll show you that in just a second. It's actually very similar to the escape velocity equation, right? The orbital velocity, so this is part B that I'm talking about right now. The orbital velocity, uh, that's an R, sorry. The orbital velocity is, it's just like the escape velocity, but you don't put the square root of 2 in there. It's just the square root of g m over r. All right, I made that square root too big, but you get the idea, right? That's how you do that one. All right. For part A, what we're going to do is we're just using this. Velocity is just distance divided by time. But in this case, the distance is there's circumference of the, if the moon is going around in a circle, and it almost is, it's almost a perfect circle. The circumference of any circle is 2 pi times its radius, right? And then we divide by the period. We'll call that T or capital T. Sometimes I put a P in there for period. That's fine too. All right, so we just have a little bit of conversion. The R can pretty much stay. We're going to need in this equation R in this equation, the second equation, R has to be in meters, right? So here, that's actually pretty simple to convert. It would be 384,400, and you just add, 3 more zeros times 10, times 10 to the third, or just put 3 more zeros, 1, 2, 3, and now that's meters. All right, so that one we're going to use down here. All right, so we're going to use that down here. All right, I'm going to use that later. For the top one, we're going to keep in kilometers, which is good. But we have to convert the period. All right, so the time or capital T here is 27.3 days, and I need that to be in seconds. So I know that in one day there are, of course, 24 hours. In 1 hour there's 60 minutes. Remember, we use MIN for minutes, reserving lowercase m for meter. 1 minute is 60 seconds. All right, and so cross that, cancels, that cancels, that cancels, that cancels. All right, very nice. So let's get the period of the moon in seconds. All right, so I'm going to do this over here. All right, let's get rid of all this. All right, so the period of the moon is 27.3 days. All right, times 24 times 60 squared, or times 60 times 60. Or I'm just going to do 60 squared. All right, equals. All right, so that's what 27.3 days is. More than 2 million seconds. All right, so that's perfectly fine. All right, so I'm going to just put that in storage right here just to make sure it's in my calculator. And then I'm going to take 2 times pi times, remember here, let me scoot this over just a little bit. We already know the distance between the Earth and the Moon. I know it's kind of strange sometimes. You see this R and you think that that's a radius. I mean, it would be like the radius of the circle that the moon makes with the Earth. That's where the R comes from. All right. At any rate, so we already did 2 pi, and then we're going to say times times the distance between the Earth and the Moon, which is 384,400. And then, by the way, that's the average distance. And then, of course, we divide that by, and I already have that in storage, the period. All right, so divided by the period. All right, and so that gives us that gives us the velocity. And notice, since I used kilometers for r and seconds for the period, that then this answer comes out to be in I guess, what do we round to 2 places past the decimal? Let me move this over. Yeah. So this comes out to be in kilometers per second. So the answer to part A turns out to be 1.02. Remember, that's what you would type into Blackboard, and of course we know that it's in kilometers per second. All right. So we're about to prove that this equation, this orbital equation in part B, it gives us the same answer. All right, so here, so now we just have to put the numbers in. So it's the square root of big G, which is 6.67 times 10 to the minus 11th times the mass of our wonderful planet Earth. Which, did I give that to you? Oh, there it is, right there. So it's kind of hidden. 6 times 10 to the 24th. Right? 6 times 10 to the 24th kilograms. That's the mass of the Earth, divided by the radius of the. The distance. So that, remember, it's orbiting the Earth. So this is the distance between the Moon and the Earth, which is in meters, which is the first thing that's the conversion that I did. So it's going to be 384,400,000, right? Because it has to be in meters. All right, so here we go. Let me get my calculator. All right, so that's the answer we got from the first part. All right, so here we go. It's going to be 6.67 times 10 to the minus 11th times 6 times 10 to the 24th divided by 384,400. And then, you could say times 10 to the third, that works too. Here, I'll show you that works, right? So exp to the third, all right? And then there's the answer. Now we have to take the square root of that, all right? And so see, it comes out to be, so the answer, by the way, comes out in the orbital velocity, just like the escape velocity comes out to be meters per second. So we take this number, 1,002. What was it? 1,020 something. Should have written it down. 20.3. This is meters per second, and then if you divide that by 1,000, you'd be in kilometers per second. All right, so dividing by 1,000, you just move the decimal place three places to the left, and so that becomes 1.02 kilometers per second, which is exactly what we got up here, right? So one is using the geometry of the Earth-Moon system, and the other one is using Newton's orbital equation. Right? Last one, this is it, okay, number 18. So they give us the size of the Earth, its radius, they give us the mass of the Earth, and it says calculate the surface gravity of the Earth. And that is a well-known value. Galileo measured this value about 400 years ago. And of course, that value is 9.8 meters per second, or also known as meters per second squared. All right, so the acceleration due to gravity is equal to big G times the mass of the object. In this case, it's the Earth, divided by the radius of the Earth, squared. All right. So the only thing is the radius of the Earth has to be in meters, right? So that's pretty simple. So it's 6,400 kilometers, and we should say 1 kilometer is 1,000 meters, or 10 to the third meters. That's the same thing. So the kilometers cancel. So this becomes 6,400, and just put 3 more zeros, and now that's meters. All right. So here we go. So it's going to be 6.67, the universal gravitational constant, times 10 to the minus 11th, times the mass of our wonderful planet, which is 6 times 10, I don't know why I wrote it that way, times 10 to the 24th kilograms, divided by, and don't forget to square this. This is the radius of the Earth, 6,400. But in meters, you got to put 3 more zeros, right? And don't forget to square this. All right, and so that should give us 9.8. All right, so let's get our calculator out. All right, and get rid of this. Let's get it so you guys can see this. All right, I'll see this a little bit better. Okay. I don't know where. All right, so maybe right about there. Right, don't forget, this is the acceleration due to gravity. Okay, and we expect the answer to be 9.8. All right, so it's going to be 6.67 times 10. Remember, you always have to use that the EXP or the EE button, times 10 to the minus 11th. That's 11th. Times the mass of the Earth, which is 6 times 10 to the 24th, divided by the radius of the Earth, but it's got to be in meters. So it's going to be 6,400 and then 000. All right. And then of course remember we've got to square that, and the answer comes out to be that's the acceleration due to gravity, right? And so if we round it to one place past the decimal, that the answer is 9.8. All right, so that's actually the answer is 9.8 meters per second squared. That's one way to say it, or you can say it like this: 9.8. Sometimes it's written this way as well: meters per second per second. So in other words, each second that goes by, something that's falling will be traveling 9.8 meters per second faster. It's the acceleration due to gravity. Gravity causes things to move faster as time goes on. All right, so that is the last of our problems. Remember, the test part B will be exactly like these problems, just different numbers.